Hello everybody, welcome to this channel. I'm Payman Hisari. In this tutorial, I'm going to teach you how to build a linear regression using RapidMiner. The steps that we're going to take is getting the data, pre-processing the data, and then apply some modeling, and then calculate the performance of the model, and finally, we'll give some tips and tricks in order to improve the performance of the model. Okay, let's get the data. The data that I have is called the housing, and the problem that we have, we are going to predict the price of a housing based on the data set that we have. Simply, I bring the data set from the data folder in the learning repository and grab and drop it in the process panel. First, I want to take a look at the data. I connect it to the output and I run the process. What I have is 545 rows of the data, and I have 13 regular attributes. The first one is the price, which is actually our target variable, and this is what we're going to predict. And the other attributes or features are the features that we're going to use in order to predict the price of the house. What we have are area, number of the bedroom, number of the bathroom, number of the stories, if it is close to the main road, if the house has guest room, does have basement or hot water heating, and does it have air conditioning, the number of parking per area, as well as whether it is furnished, semi-furnished, or unfurnished. We can take a look at the statistic as well. And here what we have is the first column is the name of the features that we have. The second column tells us the data type, whether it is integer, it's nominal, it's real, and so on. And the third column that is very important is the number of missing value in each column. And as we can see here, all of the features does not have any missing value. And the last three columns gives us some statistics about the column, depends on the type of the feature. If it is integer, it gives us minimum, maximum, and average. If it is nominal, gives us the least frequent, most frequent, and the values of different categories that exist in the nominal feature. We can take a look at the distribution as well. For example, if I click on the price, it will show me the visualization, and I can open up the visualization. And this is the distribution of the price. I can change the number of bins. For example, if I change it to 20, then I can see that the data has a normal distribution, but a little bit skewed to the right. We brought the data into the process panel. Next is to pre-process the data. Let's take a look at data again. As we can see here, some of the features are numeric and some of them are categorical. Almost all machine learning algorithms do not understand categorical variable. So we have to transform them into a numerical values. And that is what we're going to do next. In order to transform categorical variables into a numerical values, we use an operator called nominal to numerical. We bring the operator into the process panel, connect these two together, and I configure this operator. The attribute filter type, I choose all. I do not invert the selection. And for coding type, we have different methods. We can use dummy coding, effect coding, or unique integers. I use dummy coding. What it does, it creates new column for each category in the categorical variables and put it as 0 or 1. Let's take a look at the result. And as you can see, now all the columns are numeric. And if we take a look at the furnished status, it creates 3 columns and 1 column for each category that we have. one for furnished, another one for semi-furnished, and another one for unfurnished. And if you take a look at the sum of these three columns, it's always 0. And that introduces some collinearity into the model. In order to prevent that, we remove one of the columns. And in order to do that, I need to come back and reconfigure this one. And in order to get rid of those columns, I use comparison groups, and I configure this one. Edit list, so I need to add those columns. Air conditioning has two variables, yes or no. I remove no. I add another entry for basement, the same yes or no. I remove no. Add another one for furnished status. It has 3 categories. I can remove one of them. I use unfurnished. I add another category, another entry for the guest room. Again, this is yes or no variable. The same for the other variable as well. And now apply. And if I run it again, I see that the number of column reduced. And for furnished status, as we can see now, we have only 2 columns, and we removed the unfurnished one. Now that all the data is numeric, we can tell RapidMiner what column is our target variable. In order to do that, we use an operator called setRule. And we bring this operator into the process panel, connect it to this one, and configure it. And here attribute name is price for us. And the target role is label, where we tell RapidMiner this is our target variable. Next, we need to split the data into the training set and the test set. And in order to do that, we use an operator called split data. I bring a split data operator into the process panel, connect it to this one, and I configure this one. First, I need to partition it. I want to tell RapidMiner what percentage of the data is for training, what percentage of the data is for testing. I use edit enumeration. I add entry. The first entry is for the training set. I use 70% or 0.7. And I add another entry, and I use the rest, which is 30% for the test data. And here I can choose the sampling type. There are different ways. We can use linear, shuffled, stratified sampling, and automatic. Let's use automatic. Also, I need to choose the local random seed, and I choose a number, let's say choose 1. Now that our data is split, I can apply linear regression, but it is better to normalize data. In order to normalize data, I use an operator called normalize. I bring the normalize to the process panel, connect it to the split data, and I configure this one. I choose the attribute filter type to be subset, and the attributes that I want to normalize, I choose those one. I choose area, choose bathroom, the number of bedroom, the number of parking, and the stories. The rest is yes or no, and it is 0 and 1. I don't need to normalize them, and I don't normalize the price because that is the target variable. I choose apply, and I use the method z transformation. There are other methods like range transformation, proportion transformation, and interquartile range. But Z transformation, it transforms each variable into a new data set where the average is 0 and the standard deviation of that variable is 1. Next is to apply linear regression. And in order to do that, I call an operator called linear regression. I bring the operator here, connect these two together, and configure this one. And for feature selection, there are different techniques that we can use. I use M5 prime, and I eliminate collinear feature, and also I use bias. I keep the rest as it is. Now that we have our linear regression model is built, I'm going to calculate the performance of this model on training data. In order to do that, I need to call an operator called apply model. Where here I apply this linear regression model into the training data set. And this operator has nothing to configure. Next is to bring the performance operator to calculate the performance of this algorithm. And I bring the performance for regression, and I connect these two together. And I need to configure this performance. There are different metrics that we can choose. And the first metric that I choose is, actually, I'm going to choose correlation, a squared correlation, which is the R squared. And we can add other metrics that we want, but I'm taking a look at the R squared for this linear regression. I connect this one to the output, and I need to run the process. And it gives me the R squared as 0.694. 69.4% is the R squared that I get. Next, I'm going to actually calculate the performance of the model on the test data. Let's first rename these two operators. This is operator for apply model for training. And this is performance for training as well. Next, I'm going to calculate the performance of the linear regression model on the test data. In order to do that, first I need to make a copy of linear regression model. In order to do that, I use an operator called multiply. What this operator does, make a copy of a linear regression model. Now I want to calculate the performance of the linear regression on the test data. I use the same apply model operator and the performance for the test data. So simply I copy these two operators and paste it here. And I connect it using the model from the linear regression. And I rename this one to be apply model test, and the same for performance test. And I need to bring the data from a split. However, I need to apply the same normalization that I applied for the training data. And in order to do that, I bring the apply model, connect it to the normalization, get the weights from the normalization, and bring the data from a split data. So in this way, I apply the same normalization that I applied for the training set and apply that one to the test data as well. And I connect this now to the test data, and now I can calculate the performance to the output. And now I need to run it, and I get the performance for the training, which is 69%. And for the test data, we have 65%. Now that we built our linear regression model and calculated the performance on the training set and the test set, I would like to validate the assumption of linear regression, meaning validation of linearity, independence, and normality. In order to do that, first I need to calculate the residual. And in order to calculate residual, I use an operator called generate attribute. I bring the generate attribute here, and I use it for training data. I connect these two together, and I need to configure this one. The function description that I want to use is this one. I give the name as residual, and I calculate the residual as the difference between the price and its prediction. And I can find them as a special attribute, the difference between price and prediction. I apply, and if I connect this one to the output, now I will see the residual as well. And this is the residual I see. Now I'm going to take a look at the relationship between residual and the prediction in order to confirm the linearity and independence. And I use the visualization, and I use a scatter plot. And on x-axis, I have residual. On y-axis, I use the prediction. And because there is no pattern in this figure, it shows that the model is linear and residual are independent. Also, I can take a look at the normal distribution of the residual just simply by changing the bell curve. And as you can see, the distribution is normal, so the assumption of the normality is also met. And finally, I'm going to take a look at the coefficient of the linear regression model that we built and take a look at each variable to see if they are statistically significant in predicting the target variable. In order to do that, I use the linear regression as an output, and I take it from the multiply operator here and connect it to the output. And I run the model again, and it gives me this table which shows the attribute with their corresponding coefficient. And also we have the p-value for each attribute. And if we consider the level of significance as 5%, we see that only this variable has p-value bigger than 5%, which is 8.9%. So this means that this variable is not statistically significant in predicting the target variable, so we can remove it from the data set. Next, I'm going to give you some tips to improve the performance. And based on the result that we have, we get the performance on the test data 65% and performance on the training data 69%. In order to improve this, we can make sure that our target variable price is normally distributed by using some transformation. Also, we can drop outliers in the dataset that we have and drop the variables that are not statistically significant. Those are the tips and that we can apply into this model in order to improve the performance.